My name is Zhang, and my research is on gravitational field shielding by scatter field and mass radius relation for a neutron star. And my mentor is Dr. Zhang. So what is scatter field and gravitational shielding? A scatter field is a field that has no direction. There's not really much information about it. It's just, yeah, it has no direction. And gravitational shielding is a hypothetical process of shielding an object from the influence of the gravitational field. The objective is to investigate gravitational field shielding by scatter field and to develop a new mass radius relation for neutron stars that can explain the recent observations of neutron stars. And some of the recent observations were, there were neutron stars that were found to have 2 solar masses, which is immensely big. And some of them also had radius that were very small than what was observed previously. Well, right now I am basically doing this, but we will get to this later on in the program. We are comparing this guy's gravitational shielding theory. He proposed that the GQ equals this is the Newton's gravitation law, and times e to the power of -h integral rho r dr, and rho r is basically the matter density, and h is the extinction coefficient, which he proposed, well, which is measured to be very small, around 1 to the -15th power, or 10 to the -15th power to 10 to the -22 power. And since we currently do not know what rho is or how he got that, we assume that rho is constant, and therefore, and that and we also assume that the neutron star is a sphere. So then we could, well, after integration, we could get the mass equals this part right here, the 3h times the solar mass over 4 pi r squared. And we assume that the m, the mass, is 1.5 solar mass. So Dr. Zhang's gravitational field shielding theory, he obtained this. It also had the Newton's gravitation theory, plus or times this unification theory that he derived from the Kaluza-Klein unification theory, which unifies the Einstein's gravitational theory and Maxwell's electromagnetic theory. And this V is the scalar field, which is down here. And also B is not. It's just a constant. Dr. Zhang said it's supposed to be assumed as the singular radius or the minimum radius of the neutron star. And my research, I am quantitatively studying the gravitational field shielding according to Dr. Zhang's theory. I'm supposed to compare Zhang's and Majorana's gravitational shielding theories and apply that shielding theory to develop a new mass and radius relation for neutron stars. And the early results I got, this is the relative difference between Newton's and Zhang's gravitational fields, which is Gn minus G over Gn. Gn is the Newton's gravitation, and G is Zhang's gravitation. According to this graph, R is the radius, and B is the singular radius. So If R is greater than B, then there is no shielding. There's weak or no shielding at all. And if R is less than B, then there is significant shielding. And how we did that was, since R over B, for this graph, we compared, it's a phi versus R over B. Phi is the scalar field, right? So if R over B is, if R tends to B, then the phi is incredibly big, which you can see from this. If R tends to B, then phi is significantly huge. And if the scalar field is significantly huge, then G is different from the Newtonian gravitation, which means if it's different, then if it's smaller than this, then you can expect a large relative difference, which means there's significant shielding. And that goes for if phi is greater, then there's weak shielding. And here's the comparison of Newton's, Zhang's, and Majorana's gravitations. This is Newton's, which is a straight line, which shows that there's no such thing as the gravitational shielding. But for ours, we have it that as R approaches very close to 0, or there's no shielding, there's no gravitational field. It's as if the object is protected by the gravitational shield. And for here, we assume that this is Majorana's gravitation, like the data, and it's at the h equals 10 to the negative 22 and 10 to the negative 20, just to see how it compares with Dr. Zhang's gravitation. Okay, and yeah, it's to be continued.